We're going to discuss a couple of different things about the sine, cosine, and tangent functions as they relate to our right triangle, specifically the sine and the cosine. Before we do that, let's just recall this. Acute angles of a right triangle are complementary. In this case, that means the measure of angle V and the measure of angle S. Those are the acute angles that are in this right triangle. Add to 90 degrees. That's definition of complementary. In addition to that, recall using our trig ratios that the sine of angle V, sine is opposite over hypotenuse, would be comparing segment HS length to the hypotenuse segment VS length. And that's when I'm dealing with the sine, because if I'm focused on this angle, this is opposite. But if I change the reference angle to angle S, and I change the trig function to the cosine, this same side is adjacent. It's adjacent to S but opposite angle V, which means the ratio winds up being the exact same thing, because in both cases we divide by the hypotenuse, which is across from 90, and that doesn't change when I change my reference angle. Okay. That's why we know that if the sine of any angle is equal to the cosine of a different angle, we can automatically assume that those are the two acute angles of a right triangle. Therefore, those angles, angles 1 and 2, add to 90 degrees, are complementary. It's our chain rule of logic again. So again, a couple different types of problems here to illustrate that. The sine of x is equal to the cosine of 42. I'm setting the sine of an angle equal to the cosine of an angle that looks like this. We have a right triangle, one angle is x and one angle is 42. Triangle sum theorem. We know that x plus 42 equals 90. And we can go through the algebra to solve for x. Very common mistake here would be to just set these equal, but again, these are not equal. They are the acute angles of a right triangle. The sine of this angle is equal to this opposite divided by the hypotenuse. The cosine of the other angle is equal to the adjacent divided by the hypotenuse. Sine and cosine are equal. The angles are complementary. 7x plus 1 plus 2x plus 46 equals 90. If we go through the algebra here, we get x is equal to 43/9, which is about 4.78 or 4 7/9, however we wanted to look at that. In these examples, we're taking the sine of a reference angle, and we know the ratio that it represents. So what we know is three things here. We know the reference angle. We'll never reference the right angle, so we can label either of the acute angles angle R. That's the angle we're referencing. So for this example, I will label this angle R. I now also know the opposite of angle R is 9, because that's in the numerator, and the sine compares opposite and hypotenuse. And that the hypotenuse of this triangle with reference angle R is 41. Hypotenuse is always across from your 90. I want to find out the tangent of angle R. I know the tangent is the opposite over the adjacent, so what I know for sure with doing no work other than labeling a triangle is that the tangent of angle R is going to be equal to the opposite of that angle, which is 9, over the adjacent. That's what we don't know yet. And that's where the Pythagorean theorem comes in. It's leg squared plus the adjacent side squared equals the hypotenuse squared. When we solve this, 41 squared minus 9 squared, and take the square root of that, we should get that the adjacent side is 40. The tangent of angle R is 9 over 40. Look to simplify if you can. That doesn't, so we're done. Go ahead, press pause and try the problem on the right. So when we label our triangle, I selected this as angle B, so I had my 20 adjacent to it, 29 as the hypotenuse, because I'm dealing with the cosine. I need opposite and hypotenuse. I already have hypotenuse. I now need the opposite. I'll just call this the leg, the opposite leg, and that's Pythagorean theorem. Pythagorean theorem tells me that that leg has a length of 21, so the sine of angle B is equal to 21 over 29, as long as we know that the cosine is 20 over 29.